Welcome to the video lecture series for Texas A&M University course Math 150. Today we will look at section 1.2, Graphs of Equations. You can find the accompanying handouts at bit.ly/RayleneMath150. Let's begin. The objectives for today's lecture are to sketch the graphs of equations, to determine and plot the x and y intercepts of two-dimensional equations, to use symmetry to sketch graphs, to determine the equation of and sketch circles, and use graphs to solve equations in real-world problems. A one-dimensional equation is an equation involving one variable, and it can be graphed on a number line. Any value or values of the variable that makes the equation true, and by true, we mean that the right and the left sides are equal when the value is substituted into the equation. Anyway, this kind of value is called a solution. So let's consider example 1. Let's solve 3x plus 5 equal to negative 13. The first thing we want to do is recognize that there's only one variable here, so we can only sketch the solution in one dimension. For example, on an x-axis. Since the variable is called x, it is the x-axis and we will label it. If I had a variable a here, this would be the a-axis. So we solve by collecting like terms, and we get 3x is equal to negative 13 minus 5, which is negative 18, and when we divide both sides by 3, we get x equals negative 6. So you can plot some values here on the number line, and then the solution would be negative 6. We can check our solution by substituting the value that we found into the original equation and seeing if the left side equals the right side. So we have 3 times something plus 5 equals negative 13. This is a question. We are working to see if that in fact becomes true. If we substitute negative 6 in, we get negative 18 plus 5, and ultimately we get negative 13 equals negative 13, which is true. Therefore, x equals negative 6 is the solution. Well, let's try a two-dimensional equation. In a two-dimensional equation, we have two variables. In the case of graphing, we often refer to these two variables as x and y, so that x lies along the horizontal axis and y lies along the vertical axis. So an equation involving two variables is a two-variable equation and can be graphed on the Cartesian plane. Any ordered pair of two variables that makes an equation true is a solution of the equation. So for example, if we have two lines, two linear equations, and we solve them simultaneously, what we're really thinking graphically is to look for the point of intersection. So the solution here would be both an x value and a y value. And so we are getting a solution for both x and y. Now, it's possible that we have systems or sets of graphs in two dimensions where we have more than one intersection point. And if that's the case, every time the two graphs intersect, we have solutions. So it's possible to get only one solution for x and y, and it's possible to get more than one solution for x and y. And we will be looking at solving different styles or types of equations based on different functions that we will study. For now, let's consider this example. Given the two-variable equation, y equals negative 2x plus 4, let's determine whether 2, 1 is a solution. So what we're saying here is that x, y is equal to 2, 1. In other words, we're saying x is equal to 2 and y is equal to 1, which is really saying we have a system x equals to 2, y equal to 1. This bracket allows us to consider the word and. If we want to know if this point is a solution, then when we substitute x with 2 and y with 1, the left side of the equation should equal, rather must equal, the right side of the equation. So let's check. we're going to sub x equal to 2 and y equal to 1. So we have something substituted here equals negative 2 times something plus 4, and we have a question mark. So we're substituting 1 for y and 2 for x. And we end up getting that 1 is equal to negative 4 plus 4 is a question mark. 1 equals 0 is not true. Because we have false, the answer is no. 2, 1 is not a solution. What this means then is the ordered pair, or point, 2, 1 is not a point on this graph. Let's identify a solution to the equation. It really just simplifies to choosing a value for either x or y, making this a one-dimensional or a one-variable equation, and solving for the other. So let's choose an easy value for x equal to 0, so that y is equal to negative 2 times 0 plus 4, which says that y is equal to 4. So one solution, and not the only one you could have come up with, is 0, 4. So now we want to make a table of values, 3 ordered pairs, for the equation. It's the same thing as what we did in part B. So in fact, I'm already going to use when x is 0, y is 4. You can choose any other values you like for x. Sometimes it is practical to use positive, negative, and 0 values, just to get a sense of different numbers. So if x is 1, for example, y is going to be negative 2 times 1, which is negative 2, plus 4. Negative 2 plus 4 is 2. And let's try negative 3. When x is negative 3, we multiply by negative 2 to get 6, add 4, and we get 10. I'm going to change my mind about this ordered pair because on my grid I go 2, 4, 6, 8, and I don't have enough space to plot a y-coordinate of 10. So let's pick it just because the graph is already given. For the grid, let's choose a different x-coordinate. Let's choose negative 2. We substitute negative 2 for x, so negative 2 times negative 2 is positive 4, plus 4 is 8. And now we can plot these points. So when x is 0, y is 4. When x is 1, y is 2. And when x is negative 2, y is 8. We should always label the axes, put arrows on them, put an x on the right side, and a y on the top side. And we have, with a ruler, we have the line. Now we want to plot the x and the y-intercepts. Well, we actually already have the y-intercept. We found it in part B. So the y-intercept is located at 0, 4, and the x-intercept, it's not so easy without a ruler to see, so we should go ahead and try to find the x-intercept. We will see in the next slide how that is. So let's take a look at the definition of intercepts. The definition of the x-intercept of an equation as a value is the x-coordinate that makes y equal to 0. We may look at the definition of the x-intercept of an equation as a point. So this point would have two coordinates, x, y. But because the y-coordinate is 0, we know that it is x, 0. Whereas here, this is just a specific x value. So it's a single number. And so we say that the x-intercept of an equation as a point is the intersection point. Of the system of two equations described by the given equation and the horizontal line y equal to 0. So if we were looking at a graph and we have a function like this, and this is the given equation, then we would look at intersecting that with the x-axis, whose equation is y equal to 0, and we would find that we have, in this particular graph, 3 intersection points, where this is the y-axis and this is the x-axis. Similarly, a y-intercept of an equation as a value is the y-coordinate that makes x equal to 0. So as a point, we would be getting 0, y. It is also the intersection point of the given graph, but this time with the, let me put system in here, the given graph intersected with the vertical line called x equal to 0. So in this case, we have the y-axis, whose equation is x equal to 0. We have the x-axis. We have a curve. And this given curve, or given equation, intersects the vertical line in one spot. Okay, so if we go back and we find the x-intercept in the previous example, we know that we need to set y equal to 0. So by substituting y equal to 0 into the original equation, we get 0 equals, from up here, negative 2x plus 4, so that 2x equals 4 and x equals to 2. So we see that we have the x-intercept located at 2, 0. Okay, continuing on. Given the plotted point P, which is at, let's just pretend the coordinates are called A, B, and we notice it is located in quadrant 2, because this is quadrant 1, 2, going in an anti-clockwise direction, quadrant 3, quadrant 4. We can plot and state the coordinates of the point A if it has symmetry through the x-axis. What that means is we want to reflect the point A through the x-axis, reflect point P through the x-axis, and we notice that we get point A over here. What's changed is the x-coordinate, and how it has changed is the sign. So we have the coordinates negative A, B. The second part of the question says we want y-axis symmetry, so we are going to reflect the given point P through the y-axis. Let's do that again. Symmetry. Given the plotted point P at A, B below, well, or to the right, here's point P at A, B. We notice it's located in quadrant 2 because this is quadrant 1, 2, 3, 4. We start off quadrant 1 with the positive x, positive y location, and we move in an anti-clockwise or counterclockwise direction. So point P is in quadrant 2, and we want to plot and state the coordinates of point A. Point A has x-axis symmetry, which means it's reflected through the x-axis. If we reflect through the x-axis, we're going to get a point down here, and that point A has, let's put it in the right spot. Point A is going to be a mirror image through the x-axis, and the x-coordinate hasn't changed. We're still going the same spaces to the left, but instead of going b spaces up, we are going b spaces down. So the point A is located at little a, negative b. In part B, we're taking point P and reflecting it through the y-axis. So we're going to go a mirror image to the other side, and we're going to get point B is located the negative or opposite number of x spaces, but the same y coordinate. And so point B is located at negative a, positive b. And lastly, point C has origin symmetry, which means that if we put our finger on the origin and rotate it 180 degrees, this point would end up located in quadrant 4. Another way to talk about origin symmetry is that you could perform a reflection through the y-axis and then a reflection through the x-axis. You can also do those in reverse order. So if we do that, origin symmetry gives us a point over here, and that is point C located at negative a, negative b. Okay, so in general, a reflection means to change the sign of the x-coordinate of all points. Well, this would result in changing the sign of the x-coordinate means that we have gone across which axis if we change the sign of x? That would be the y-axis. And we are changing the sign of x going from left to right, so this is a horizontal reflection. And let's just clarify that that's through the y-axis. A lot of students have trouble with that, but they forget that the y-axis is a line whose equation is x equal to 0. Similarly, changing the sign of the y-coordinate of all points in the graph results in a vertical reflection. Y is the vertical coordinate, so changing the sign of the y-coordinate changes from top to bottom or bottom to top. So if we do a horizontal reflection of the point pi comma negative 3, horizontal means change the sign or change x, and reflection means to change the sign. So the horizontal reflection of that point is negative pi comma negative 3. We don't change the y. The vertical reflection of the graph whose equation is this, well, this means we want to change the sign of y. Now we notice that y is the result of something coming out of absolute value. So we may want to consider the graph of this, and we will do that right now using a graphing program called Graphing Calculator. You can find this in Graphing Calculator program. You can find it in apps.qatar.tamu.edu. Under the Maths folder, Mathematics and Engineering, I believe. And you need to open up the Citrix process. So look for that, and let's see what happens when we open this up. I want to take a look at first the graph of y equals x squared minus 4. I like blue. And I'm just going to center it. You can use the drop-down menus to see how that is, and I'm going to zoom out. And if I take the absolute value of any quantity, we know that the absolute value makes something positive. Well, in the event that x is less than negative 2, we have all of this portion of the graph. And this portion of the graph here has y-coordinates that are already positive. So the absolute value of these y-coordinates, 6, 5.5, 5, etc., won't change. Similarly, over here, the y-coordinates are positive. You can see we've traced, and this is a y-coordinate of 5.1. So taking the absolute value of that y-coordinate won't change. But taking the absolute value of these y-coordinates, which are negative 0.3, negative 1, negative 1.5, negative 2, negative 4, these y-coordinates will change. So the result of taking the absolute value of x squared minus 4 is to produce a graph which is almost the same as the original graph, at least on the outer two branches. The inner portion has been reflected vertically through the x-axis, or through the line y equal to 0. So the vertical reflection of this graph should have everything lying below the x-axis. So a vertical reflection, if you recall, just means that we are changing the sign of y. So if we change the sign of y, we get this, or we could rewrite it as y equals negative absolute value of x squared minus 4. Okay, talking about reflections suggests we should talk about another type of transformation called a translation. Adding or subtracting the same amount from all x coordinates of a graph results in a horizontal, because it is an x change, translation, while adding or subtracting the same amount from all y coordinates of a graph results in a vertical translation. So if we were to perform a horizontal translation, right 3 spaces, and a vertical translation down 4 spaces to the point, we want to perform this, let's say, on the point negative 3, 5. So this means we want to add 3, and this means we want to subtract 4 because we're going down. But what we do have to be careful is this is adding 3 to x, and this is subtracting 4 from y. So if we do that, horizontally translating right 3 spaces takes us to an x-coordinate of 0, and going down 4 spaces takes us to a y-coordinate of 1. We're going to leave example 5 to work on in the problem-solving session, but feel free to take a look at it on your own. And that's all for now.